There we go. And good evening, everybody. This is Paul NO0T from the Front Range 6 Meter group, and have a good crowd tonight. And we've got one of my favorite guys, W3LPL, who's got a huge antenna farm in Maryland. He's got more aluminum in the air, I think, than Alcoa. And anyway, we wanted to welcome him tonight. He's going to give us a great talk. I saw part of his talk back in Dayton about 3 or 4 years ago, I think it was, and that's when I first learned about some of the most interesting things about 6 meters. Was like there's actually a guy who puts up all these tables, and that's where I learned about Lionel. Was through Frank's presentation there. Plus, I also learned my antennas were always too high. So now we're going to explain why antennas need to be at a certain height for 6 meters in order to get some ground wave, or ground gain rather. So without any further ado, I'm going to mute everybody except for Frank and let him carry on here. And then at the end of this, if Frank has time, we could maybe entertain some questions and some answers, hopefully. So with that, over to you, Frank, and take it away.
Okay, so screen sharing is enabled for me, I guess?
Stand by. I knew there was something I needed to. Yeah, I think so. Yeah, so it's clicked.
Do you see my screen now?
No. Let's see. What am I not doing?
Oh, let's see. There's one more thing. You see it now?
There it is. There it is.
Okay, we should be ready to go then. And then we should be full screen.
You are.
Okay, well, thanks very much for inviting me to join you this evening. And this is a somewhat enhanced version of the presentation you saw at Dayton probably 3 years ago, I suspect. This photograph is my primary 6-meter antenna. It's an 11-element Yagi on a 60-foot boom, 50 feet high. And it's a truly remarkable antenna. Had a lot of fun with it over the last several years since I installed it. Just a few examples. Mostly on 6 meters, I'm a DXer. I get on for the contests, and I also work some grids when it's convenient. But my main interest is the sporadic E DX, which mostly occurs in June and July. There are certainly exceptions to that, but June and July are the primary times. And it can be quite remarkable. The last 2 years, I worked more than 500 Europeans each sporadic E season, and more than 100 JAs each sporadic E season. So this antenna really works. So this perhaps is the most important takeaway from the whole presentation. Anybody who doesn't own the AWR antenna book really should go out and purchase it. You can either buy it through the league, or you can buy it on Amazon, or probably other places too, DX Engineering. But it's well worth every penny spent on it. And the editors in recent years have really gone out of their way to improve the content. So if you own the 23rd edition, well, it's an old one. The 24th is better. And the authors are working on an improved version already. So let's just set the groundwork here. In this presentation, all of the gain figures shown, and this corresponds with Lionel's presentations, are all measured in terms of gain relative to a half-wavelength Yagi. And a half-wavelength Yagi, by definition, has 2.15 dB gain over a theoretical isotropic radiator. And that little illustration on the left shows why it has gain, because its signal is concentrated broadside to the dipole, and there's essentially no radiation off the ends or near the ends. So it has gain because that additional signal has to go somewhere, and it reinforces the main lobe perpendicular to the dipole, and it gives you 2 dB of gain. So and there's one slide that's an exception to this, and I'll point that out. But apart from that, every gain figure shown in this presentation is with respect to a half-wave dipole at the same height above ground. So in order to kind of understand where we want to put our antenna, it's helpful to have some idea as to what the required elevation angle is. That is the radiation angle above the horizon at which we'd like to direct most of our antenna pattern. And this is some very excellent work done by Carl K9LA. There's a link to his paper at the bottom of this slide. It gives a lot more detail as to why these are the preferred angles. But a couple of things is that FOES, that's the vertical maximum frequency for sporadic E propagation, and the low angle MUF is about 5 times what the vertical incidence is. So for most propagation on 6 meters, and in fact, by far the majority of sporadic E on 6 meters is at about 10 degrees or below. On rare occasions, it's at 15 degrees or higher. You can tell when these occasions are because there might be a 2-meter opening. But if your interest, like mine, is in DXing, these really high angle occasions aren't that important because they cover very short distances. So for a DXer, it's desirable to have your antenna at least 25 feet high. And I'll show you how much of a benefit there is to going to 50 feet. And in a little while, I'll show you how much it costs you to go significantly above 50 feet, just because of the way the sporadic E propagation operates. And my experience, I have several 6-meter antennas, and at one time I had a 3 Yagi array where I could switch the elevation angle. And my consistent experience from Maryland is that takeoff angles at about 5 degrees. I never had enough resolution to say whether it was 5 degrees or 7 degrees or 3 degrees, but definitely not 10 degrees. Radiation angles of about 5 degrees are definitely preferred from Maryland and the nearby areas for long haul propagation, whether it's to Japan or the Persian Gulf or anywhere in Europe. That's a real magic number. I have another Yagi that's 150 feet high, and it's, I would say, never as effective as the lower Yagis. It's a useful antenna, but it's just not as effective as the low ones. And further compounding matters is that when you think about the effectiveness of antennas, you also have to think about what kind of antenna your partner in any particular QSO is likely to be using. And darn few of those are using antennas at 100 feet. A few of them are, but very, very few. So when you think about the responsive antennas at both ends of the propagation path, you're much more likely to have antennas that radiate at 5 or 10 degrees and not way down at 2 degrees or maybe 3 degrees. And I think I mentioned that Carl's presentation is referenced here at the bottom. So let's look at some radiation patterns, elevation patterns of some common Yagis. And in this presentation, I'm not going to focus on huge antennas. Those of you who are listening to this presentation that have huge antennas, like maybe my 11-element Yagi, you don't need the information that I'm going to present to help you understand why that's a good idea. And I'm not going to bore the vast majority of the audience by comparing the performance of various 9 and 11 and whatever element Yagis that are available. Because for the typical sporadic E user, you don't need that sort of stuff. And I'll mention a little bit as to why it's somewhat helpful, but it is not a game changer. The real game changer is having an antenna at roughly the right height. 50 feet is not a magic number compared to 45 or 55, but it's a very, very effective height. And here's why. You can see it in this chart. This chart is directly out of EasyNet, which, by the way, is now a free program. It's a really fine program. It's worth investing some time to learn how to use it. It used to be moderately expensive, but now it's free. But you used to be able to get support from W3LPL, but that's no longer available. He has now retired, so there's some loss of value because even though you don't pay for it, you also can't get support from him. So this is what the radiation looks like from a typical 5-element 6-meter Yagi, 50 feet high, same height as my big 11-element Yagi. Its main lobe is focused at 5 degrees elevation angle, and it has very useful radiation, only 3 dB down from just under 3 degrees all the way up to almost 9 degrees. So it covers pretty much the whole range of angles that are of interest to a 6-meter sporadic DXer. So let's take a look at a few other examples. This is the same Yagi down at 25 feet. And those of you who've used antennas only 25 feet high, they work remarkably well. And the reason they work remarkably well is they're only 3 dB down from an antenna that's 50 feet high. So yeah, you're giving up 3 dB, but that's not the end of the world. You can still work the world on sporadic E with an antenna that's 25 feet high. And another interesting thing about it is that first lobe, and there's a name for that lobe. It doesn't appear in amateur antenna books yet. I suspect it might in the next edition of the ARRL handbook. But that first lobe is caused by a reflection from what is known as the first Fresnel zone. And I'll explain that in just a moment. So that's where that lobe is created on the ground. And it's a very wide, when you're down to 25 feet, the good news is that that first lobe is very broad, covers almost 8 degrees of beam width. Unfortunately, its maximum gain is a little bit higher in angle than you'd prefer, but the penalty isn't very great. It's only about 3 dB. So I don't ever encourage or discourage people from putting up 6-meter antennas because they can only put them at 25 feet. You can have a lot of fun with a 25-foot high antenna. And 25-foot antennas are not that difficult to install if you can only do it away from your own home. You can find a place in a park or hilltop or waterfront. And if you can put up a 24-foot mast and a rotator and a little stub, you're ready to go. And that's the kind of antenna that you can install yourself without a great deal of difficulty. So now let's take a look at a really high antenna. This is a 100-foot high antenna. And this kind of same problem applies to antennas that are much over 70 feet high. You can buy your own copy of EasyNet and see for your own antennas what's going on with this same chart. And the problem with very high antennas, the most important problem, is that the first deep null occurs exactly at the elevation angles that we most want. So this antenna, the same 5-element Yagi I showed you at the other two heights, the same 5-element Yagi is down 3 dB at just over 4 degrees. And then the prime elevation angles we want for sporadic E multi-hop DXing is from 5 degrees to 10 degrees. And it's got almost no useful radiation from just over 4 degrees to about 7 degrees. That's prime territory. And then it's got a little narrow lobe up there in the primary area at about 8.5 degrees. And then it's back down into a deep null at 10 degrees. So this is a horrible antenna. It works, but if you compare it to something at a more suitable height, less than 70 feet, then it becomes very apparent to you that the 100-foot high antenna is a really bad choice. And by the way, these charts are for flat Earth. But if you're lucky enough to be in a location that has sloping foreground, the bad news is that your antenna needs to be lower, because whatever that slope is over the distance of the Fresnel zone, which I will explain in a moment, whatever that slope is subtracts from these angles. So if you've got let's say a 2-degree slope over a 2-mile range, then we'll go back to this. Oops. to this ideal antenna. If you've got a 2-degree slope, well, your maximum gain is now down at 3 degrees, and you've got a deep null at 6.5. So your antenna, if you have sloping foreground, really needs to be more like 25 feet high rather than 50 feet high. Okay, so let's take a look at another set of data that Lionel uses in his charts, and that is front to rear ratio. A lot of us have heard about front to back ratio, and front to rear ratio is getting to be a little more popular. And this chart explains the difference. In the classic definition of front to back ratio, it would be exactly the ratio between the signal directly off the front of the antenna to the signal coming directly off the back 180 degrees behind. And for many antennas, the main undesired lobe off the rear of the antenna is not directly off the back at all. So the more effective measurement to use is front to rear, and that is defined to be the main lobe, and that compared to the strongest lobe in the rear 180 degrees of the antenna. And you can see why you wouldn't want to include the second lobe, because usually in a well-designed antenna, the second lobe, which right here is 45 degrees off the main lobe, it's usually stronger than the rear lobe. So if you said main lobe ratio to all the other lobes, well, the rear wouldn't dominate, it would be this second lobe. So it's the definition that Lionel uses, and it's widely used, as main lobe to all of the lobes off the back 180 degree of the antenna. So that's just a matter of definition, because that's what Lionel uses, and it's the correct thing to use. So let's look at ground gain, because what we're trying to do when we install antennas near the ground, 25 feet high, 50 feet high, or maybe mistakenly really high, what we're really trying to do is to take advantage of the gain that is produced by the reflection off the ground. And I'll show you a little bit what that looks like in the next couple of slides. But there's a price to be paid here, and that is in order to maximize that possible 6 dB of gain that comes from the reflection, it's necessary that Fresnel zone, and I'll show you the size of that zone, it's necessary that it be relatively clear of obstructions. The more obstructions there are in that zone, the less gain you're going to achieve. You'll still get some gain, except in the most severe cases, which would be kind of a urban or industrial area with lots of buildings. But apart from that, even if you're surrounded by forest, you probably get 3 or 4 dB of gain, but you probably won't get the entire 6 that is possible if you're in a rural location with very little obstruction over the couple of miles in front of the antenna. But it isn't just obstructions. The other thing that costs somewhat against that possible or ideal 6 dB gain is terrain irregularities. So, you know, most people who live on mountains and hilltops tend to have lots of terrain irregularities in the first couple of miles in front of the antenna. So that also comes with a cost and subtracts away from that possible 6 dB of ground gain. So there was a station here in Maryland who was located right on the Chesapeake Bay, literally just a few dozen feet away. Normally, the Chesapeake Bay is just as flat as can be for miles and miles. And he was able to consistently work things that no one else could. Apparently very low angle stuff, and he was able to eke out every possible one of those 6 dB of ground reflection gain figures. So let's look a little bit more at what the Fresnel zone actually is. This figure has never appeared in any amateur publication that I'm aware of. Professional antenna designers are well aware of it. Professional people who design point-to-point microwave links are well aware of it. Even some repeater builders are well aware of it, but it has never appeared in the ARRL antenna handbook, and I suspect it might appear in the next one. So what is this? So when a electromagnetic wave is radiated from an antenna, it produces a direct wave from the antenna directly up towards the ionosphere, towards the sporadic E layer, mostly what we're interested in on 6 meters. But the antenna, of course, has doesn't have a pencil beam oriented only towards the ionosphere. It also radiates down towards the ground, in the foreground in front of the antenna. And the question people always have, well, how big is this Fresnel zone? And I'll get into that in the next slide, but let's just define what it is. There's a point here called the reference reflection point. I'll define that on the next slide, but that is the center of the most effective part of this reflecting region. So it sits out in front of the antenna, and I'll show some very specific numbers on the next slide. So that's the main part. It turns out that most of the effect of the Fresnel zone is in kind of the middle half of this region. So kind of in here. So most of that 6 dB occurs in this region about halfway out to the edge. And then of course, the most important part is right at this reference point. But there is still contribution to the 6 dB of ground gain all the way out to the edge of the zone. And what happens at the edge? And there are four, well, of course, there are edges all the way around this, and it's an ellipse. But the most extreme edges are the far edge in front of the antenna, and that's much, much further away than the near edge, which is near the antenna here. And then there's a left and a right edge. And so many people say, well, how can there be wouldn't that just be a point? No, it's not. Because we're dealing with radiation to the ionosphere that's, let's say, 1,000 miles away in front of us. And we're dealing with electromagnetic waves at 50 megahertz. We're not dealing with a laser. So we're not dealing with a single point on the ground. In fact, it's a reflecting zone. And its width is not terribly wide. I'll show you that in just a moment. So the first lobe, so the first Fresnel zone is the reflection zone that corresponds to the lobe that we're most interested in. Let me just go back a bit. So it corresponds to this first lobe, and we should be designing our antennas primarily for the effectiveness of that first lobe. And that's the first Fresnel zone, whose dimensions I will give you in detail in just a moment. So that's the area we're interested in. We're especially interested in kind of the middle half of the area of that zone. But ideally, if we want every single possible dB out of that 6 dB, we really care about almost the whole thing. And we really would like it to be perfectly smooth. That's not very realistic. And also free of obstructions. That's not very realistic either. But in general, this is what we'd like to shoot for if we can. And that would be to have the obstructions in front of the antenna no larger than a quarter of the height of the antenna. So if you're in an urban area, for example, you don't want to tuck your antenna down among the buildings. You'd like to get it 2 or 3 or 4 times higher than all the surrounding buildings. And then the effects of the obstructions are significantly reduced. Now, if you can't do that, that doesn't mean you can't operate 6 meters. It's just that your competitors who can do this are going to have a few dB advantage over you, but can still have a good time on 6 meters, even if you can only put up your antenna 20 feet high and it's tucked in among buildings, it'll still work. It's just that there's a penalty. And why is this a problem? Because the terrain irregularities and obstructions within that reflecting zone, the Fresnel zone, produce unwanted phase shifts, in some cases absorption, unwanted reflections and diffractions that reduce the ground gain by, in less severe cases, a few dB, but in severe cases, like in an urban or industrial setting, it can really wipe out most of it. And one of the worst cases is in a mountainous area where you've got mountains in front of you that actually block some or all of these rays that I show here. So a mountainous situation can be pretty severe. And if you're operating portable, you'd really like to select a location where you're not badly affected by irregularities in the mountain terrain in front of you. Not to suggest you can't operate from those locations, you just don't get the ground gain you'd like to get. Now, not everybody can operate from the shore of the Chesapeake Bay either, but that's a darn good place to operate from. So let's get very specific now about this reflecting zone. And keep in mind that these are the dimensions right to the edge of the zone, and you really don't have to, when you get near the edge of the zone, those are the last few tenths of a dB of gain. So you don't have to have absolute freedom of obstructions and terrain irregularity all the way to the edge, but it's nice to do it if you can. But certainly in the middle half of that, so let me just drop down to the bottom here. So at this 5 degree elevation angle corresponding to kind of this magic 50-foot height for 6 meters, at least from the East Coast. But keep in mind, I work plenty of JAs with this 50-foot high antenna from the East Coast also. So the Fresnel zone occupies about 15 acres for a 50-foot high antenna. So what I'm suggesting is that if you can, try to get the middle 5, 6, 7 acres as clear as possible when you site your antenna. And it won't matter that much if the remaining 10 acres in the Fresnel zone isn't ideal. So let's focus first on the 5 degree case, because that's at the fairly optimum height of 50 feet. So what we'd like to have, if we can, is to have the terrain roughness in that Fresnel zone, and I'll mention the dimensions here in just a moment, less than about 12 feet. And how big is the Fresnel zone? Its width the size of the Fresnel zone is highly dependent on the height of the antenna above ground. So there's a disadvantage to going to 50 feet rather than 25. And that is at 50 feet, the Fresnel zone is much bigger than it is at a much lower antenna height. And on the other hand, if you put the antenna very high at 100 feet, which I do not recommend, the Fresnel zone is huge. And you're much more concerned about dense forests or suburban development over an area of 100 acres. So again, going back to the 5 degree case, which is kind of the sweet spot for these 3 heights above ground, the width of the Fresnel zone in front of the antenna is 280 feet wide. It's 140 feet left, 140 feet right. And of course, that's in the direction that the antenna is pointed. So that's not that big an area or that big a dimension at a height of 50 feet. The reference point, which is the point that I mentioned where the most efficient reflection takes place, is 570 feet in front of the antenna. So that's the most efficient point for 5 degree elevation angle ground gain reinforcement. So that's quite a ways in front of the antenna. And the far edge that contributes a little bit to the ground gain is 3,300 feet in front of the antenna. And the size of that Fresnel zone is 15 acres. Well, so you'll get the full 6 dB of possible ground gain if this whole area is smooth within about 12 feet, and if the obstructions are less than 12 feet high, and if these obstructions that do exist that are larger than 12 feet high occupy less than about 5% of the Fresnel zone. This is not your typical suburban location, obviously, but there are quite a few ham locations that are in rural areas that come pretty close to this. It's pretty easy, by the way, to get about 4 dB of ground gain. You can violate a lot of these ideal conditions and still get 4 dB, but you're not going to get 4 dB of ground gain if you're nestled in an industrial area with large buildings, or if you're in an urban location, you're just not going to get that 4 dB. It's just not possible. So let's look at the case of a 25-foot antenna, and you notice the Fresnel zone in front of that antenna is only 2 acres. That's a pretty small area. So if your antenna is, if let's say you're going to a portable location and you want to locate your antenna, well, you'd ideally like to pick a place where about the 2 acres generally in front of the antenna is meets as many of these obstruction criteria of buildings, for example, and terrain smoothness possibilities as you can, because it's only 2 acres. And on the other hand, if you're putting up an antenna that's 100 feet high, that Fresnel zone is massive. And the sweet spot in the kind of the middle 50 acres is also massive. So there's a possibility of having more degradation on top of having the antenna too high. The ground reflection from the Fresnel zone actually can be pretty inefficient. So let me just reinforce a couple of things here that we're interested in. The center of the Fresnel zone, where the most efficient reflection occurs, but only a tiny amount of it, is about roughly 1/3 of the way out. And the width of the Fresnel zone depends only on the antenna height, and it's pretty modest dimensions, even for a 100-foot high antenna. The near part of the reflection is relatively close to the antenna, unless the antenna is very high, 100 feet too high. And the far end of the reflection zone is surprisingly far away if your antenna is very high, 100 feet high. The far end of that Fresnel zone is more than 2 miles away. Okay, so let's get on to some specific cases of antennas that are available for us to acquire. So this is extracted from Lionel's most recent chart, published last month. And I've just chosen a few of the more interesting, I think, antennas that are in that chart that are relatively small. So these are suitable for a location where you don't feel comfortable with a large antenna, or if you prefer a smaller antenna for friendliness with neighbors. And all of these antennas are suitable for portable use as well. They're not that heavy, and I'll show the weights in a moment. And some of them are really high performers. And you'll notice in the type of the antenna, and this is all the designations that Lionel uses, that the 3 antennas that are shown with front to rear ratio in red are all called LFAs. I'm sorry, 2 out of the 3 are LFAs. They're loop antennas, and I'll show you a photograph of those. The driven element is a loop, rather kind of like a fat folded dipole, rather than a simple dipole feed. But interestingly, one of the antennas in Lionel's list is one of the very fine antennas designed by YU70F. By the way, my 11 element Yagi is designed by YU70F. And this Yagi, simple Yagi with a simple split feed, has a remarkably good front to back ratio for a compact antenna. So this is a very easy antenna to build. You don't have to worry about bending aluminum to create the loop. And a very practical, lightweight, relatively lightweight antenna to build. And I've also included a 3-element Yagi here, just to show that a small, very lightweight 3-element Yagi can still be a pretty effective antenna for use by a temporary portable operation. This antenna has a boom length of only 7 feet. The front to back ratio isn't that great, but if you're in a portable location, maybe it doesn't need to be. And the gain is a bit lower, but only a couple dB better from the very best antennas shown in Lionel's chart. So let me just back up a little bit and make a comment about Lionel's chart that he publishes several times a year, updates several times a year. Number one, I like me and many other 6-meter operators and other operators on the other VHF bands, and people do EME and other modes also. Lionel does a great service to us because there's no bias towards any one of these antennas versus another. This is Lionel's best case effort to model those antennas equally. And it's a very fair judgment between them. So you don't have to compare the manufacturer's numbers one to another to try to figure out which one is the most proficient liar. You can use Lionel's charts and see this exact same data for yourself. But I'll also mention that one particular manufacturer, G0KSC, who sells his antennas under the Innov Antennas trademark or trade name, he has many, many antennas that he offers for sale that are not in Lionel's chart. So apparently he has not shared the details. But I have elected not to show any of Justin's antennas for which Lionel does not have data, because it would just skew the whole thing, and I wouldn't know how to judge Justin's data versus Lionel's data. So the antennas that Lionel doesn't have the data from G0KSC or Innov antennas are not shown in any of these charts. Doesn't mean that Justin's antennas not shown in these charts. It doesn't mean they're not good antennas. It just means Lionel doesn't have the data. And these G0KSC loop fed arrays are excellent antennas. So if you're thinking about buying one of those antennas, for example, it'd be a good idea to contact Justin and have a conversation with him, and after that discussion with Justin, decide which is the best antenna for you, rather than going only after the subset of antennas that Lionel has data for. Okay, so I'm going to show you a couple of these, I'm going to show you all of these antennas that are shown in this chart. So these are relatively compact antennas. And the first one is the M-square 3-element Yagi. This antenna weighs only 6 pounds. So this is a really practical antenna to put on the end of a 24-foot mast. You can probably erect this antenna in a portable location in less than 10 minutes. Most of that time would be attaching the elements to the boom and attaching the feed line. This is a really nice antenna for portable operation. Yeah, its front to rear ratio isn't that great. And its gain is down 1 or 2 dB from other antennas. But I'll tell you, when you're in a portable location, you're not going to be able to tell the difference between 1 or 2 dB of forward gain between this and any other antenna that's practical for a quick, easy install at a portable location. So this little antenna is worthy of consideration because it's so small and lightweight. But the other antennas that are somewhat bigger are, not surprisingly, a little heavier and better performance. So this is an antenna made by E Antenna. It's also a loop-fed Yagi. So it has really nice front to rear ratio. It weighs about twice as much as the 3-element Yagi I just showed you. And all of these loop-fed Yagis look the same as this one. So you see that the loop feed on the right-hand side there, and the remaining elements are Yagi elements. You can buy this one from DX Engineering. And this is a bigger loop-fed Yagi. It's a 14-foot boom, weighs 17 pounds, and also has very good front to rear ratio. By the way, you'll see that these front to rear ratios get better with much bigger antennas, but these are pretty respectable numbers for a small antenna. And this is the YU70F. It's the only one in this category of antennas that does not use loop fed. So he did a pretty remarkable job optimizing this antenna, getting 24 dB of front to rear ratio with a simple split dipole feed. This antenna would be very easy to build yourself. It would work really well on a 24-foot mast or on a 50-foot mast. And this is one of Justin's G0KSC's antennas. It's almost 20 dB of front to rear. Very clean looking antenna, you can see in the photograph. Every one of these photographs includes the link to the detailed description of the antenna. In many cases, the manufacturer also includes a manual, so you can see in detail how these antennas are built. So let's look at some bigger antennas. And the main takeaway from this is that when you go to somewhat larger antennas, the front to back ratio increases by 4 or 5, 6 dB, just by virtue of the longer boom. Well, if you look at Lionel's data, you'll find some antennas with 20 to 30, 40-foot booms that have rather poor front to rear ratio performance. And I didn't include any of those here. But these are all quite good. They're heavier. That's not a surprise. Anything, and the weight is listed on the next charts, but anything from about 15 to 30 pounds or maybe a little bit more. And you'll notice the G0KSC antennas are here and his Innov 8LF8, which is a fabulous antenna, absolutely fabulous antenna, but it's a 40-foot boom. And as I mentioned earlier in my presentation, I did not include any of the gigantic antennas that are in Lionel's presentation, like the 11 element Yagi that I use, because very few people are interested in antennas of that size. And honestly, the benefit is very small, very small. So these are all LFAs with one exception, and that's the very popular M squared 6 element Yagi. And I'll show you in a moment why this is very popular. It's very lightweight. So if you're going to go on a portable operation, this lightweight antenna is worthy of consideration, but its performance is down a bit in terms of front to rear. By the way, why do we really care about front to rear? If you're getting signals coming in from one hop sporadic E or from nearby hams, those signals can be enormous. And if you're in the FT8 band, that band gets pretty crowded with very strong signals. So front to rear ratio is more important than ever for those of us who operate on the FT8 modes. So this is really important, and especially if you're in a metropolitan area where there might be other stations within 30 or 40 miles that are running kilowatt power and effective antennas at 50 feet or higher. And you can see also the cost of these antennas, not surprisingly, is higher. So let's take a look at these individual antennas one by one. So this is very effective. This is the best front to rear ratio of any of G0KSC's antennas in Lionel's listing of antennas. And it's not a terribly heavy antenna. It's 14 pounds, 21-foot boom, and the gain is really good. Well, let me just go back to the other chart. So if you look at the gain figures here, if you recall on the other chart, for the small antennas, most of them had 8 dB of forward gain. This G0KSC antenna sacrifices what might be 10 dB of gain to get only 9 dB of gain. I say only 9. I defy any of you to tell the difference between a 1 dB antenna. But in return for that, Justin got 30 dB of front to back ratio. But most of these antennas only have 2 or 3 dB of benefit over the much more practical antennas that I had just shown. So this is that 30 dB front to back ratio G0KSC antenna. And here's one that he sells under his Innov Antennas brand. Almost the same performance, 1 dB of more gain and 3 dB of lost front to rear, not much of a difference there. By the way, I'll just point to you see the balun? If you look at the loop fed, many of these antennas use coil coax balance. They're pretty good. Not state of the art by any means, but they're pretty good, and I'm sure they work fine in almost every case. If you look at these photos, you'll see probably most of the antennas are using coiled coax. Chokes is a more appropriate term. This is a much heavier antenna by E antennas. It's not much difference in terms of gain in front to back, but it's an excellent antenna. It's loop fed. And this is another one of Justin's antennas, and it's part of a massive array that W3LPL installed some years ago with 6 of these antennas. I will tell you, only a few people have built these huge rotating towers with very large numbers of 6-meter beams. And at least one of these was taken down shortly after it was built because the owner discovered, just as you might guess from the early part of my brief presentation, that only rarely do the very high antennas contribute anything of value to an array like this. So my recommendation to people who want to put up an array of stacked Yagis is to put up a shorter rotating tower, certainly no more than 100 feet high, with 2 or 3 stacked Yagis, and forget about this stuff of using 6 stacked Yagis on a 150 or 200-foot tower. It's just not worth the enormous effort. This is another one of the E antennas Yagis. This is a 50-foot antenna, and that's a much longer boom, 31-foot boom, but very nice front to rear, and gets another dB of gain. And this is the M square. This is a very popular antenna. It uses a T-match fed dipole Yagi. which you can barely kind of make out in this not very good photograph. But this is a really good antenna. 21 dB front to back it's probably okay, except in metropolitan environments where it'll be susceptible to really strong signals from other FT operators, especially FT8 operators. But this antenna, because it weighs only 18 pounds, is practical for a more ambitious portable operation. But it only has 3 dB gain over the much more practical 5-element Yagis, and it's not clear, unless you're doing AME, that it's really worth the effort to put an antenna like this up in the air. And this is the 8-element loop-fed Yagi that Innov Antenna sells. It's really an incredible antenna, but it's big. It's 38-foot boom. It's heavy, 40 pounds. And if anybody's ever worked JA1BK, he's very, very active on 6 meters. This is why. He's so strong and so easy to work. He's got a pair of these stacked Yagis on a crank-up tower. This is among the antennas with less than 40-foot boom length. This is definitely the best one. So let's look at how you might go about building your own antenna. 6-meter antennas are really easy to build. You can buy the materials from DX Engineering. You can buy the tubing that's already slit, as you can see in this photograph. And for the tips of the elements, you use a smaller diameter tubing, which you can also buy from DX Engineering. And of course, you can buy it from local suppliers as well. But this tubing is shippable by UPS, so it's very, very convenient to purchase it from DX Engineering if you don't have a favorite supplier in your metro area. And in terms of building booms up to 24 feet long, you can also purchase that tubing from DX Engineering in 6-foot lengths, so they're shippable. Or you could purchase longer lengths from an aluminum supplier in your local area, if you prefer to go that way. Square aluminum tubing is becoming more popular now, and here's a couple of dimensions of square aluminum tubing that you can use. And you can purchase this from, among other places, from Metals Depot. The advantage of square tubing is it's a whole lot easier to get the elements very precisely aligned on the boom. Quite frankly, it doesn't really matter if the antennas are if the antenna elements are a little bit tilted a few degrees with respect to other elements. Nobody will ever know, but maybe it won't look quite so pretty in your photograph, but the performance isn't affected if the alignment isn't perfect. These clamps have become very popular for mounting Yagi elements on a boom. They're made by Stauf, German company. Many companies sell these. I've just listed one of them shown here, but you can look on Google and find a number of suppliers for these clamps. And the way I prefer to mount these, my 11-element Yagi, so these are mounted to in my case, they're mounted to a flat plate, but rather than making the flat plate out of aluminum, it's made out of phenolic, a popular type of plastic. So the only conductive items in very close proximity to the 6-meter elements are the 2 stainless steel U-bolts that go through these clamps, and the 2 U-bolts that attach the plate, the phenolic plate, to the boom of the Yagi. So there are no conductive aluminum plates at all near the Yagi elements. There's nothing wrong with using aluminum plates, but they do have somewhat of an effect on the dimensions. So all of these antennas that I showed you, with the exception of the M2 7-element Yagi, all use split dipole feeds, including the LFAs. The one side of the LFA is open, and it's a direct 50 ohm feed. But you definitely don't want to connect your coaxial cable directly to the feed point of the Yagi, and here's why. Sometimes I ask hams, how many conductors are present at the end of a piece of coaxial cable? And of course, everybody says 2, the shield and the center conductor, but that's absolutely false. There are 3 conductors at the end of every piece of coaxial cable. There's the center conductor, there's the inside of the shield, and there's the outside of the shield. So there are three conductors. And the main problem with connecting a piece of coaxial cable directly to the split feed of any of these Yagis I showed you is that any RFI received as a common mode current on the outside of the coaxial cable gets conducted into the driven element and then into the entire array. So you've paid all this money or put in all this effort to build an antenna with great front to rear ratio and with minimum side lobes, and then you've degraded it by not putting a suitable choke at the connection of the coaxial cable to the driven element. And this just illustrates kind of a worst case situation where the current on the coaxial cable is very high. And as a result, the current on half of the driven element is very low. Most cases are not as severe as this. And for the most part, what we're worried about here is the receiving performance of the antenna, not the transmitting performance. So this problem doesn't affect the gain of the antenna to a very great degree, but it definitely affects the receiving performance of the antenna, potentially to a very large degree. Let's look at a couple of these. So I pointed out in one of the photographs I showed you the use of a coiled coax choke. They're reasonably effective. And in a relatively quiet RFI environment or an environment that's not in a metro area, we have very strong signals from other powerful 6-meter stations. This is a very effective way to go. It's very inexpensive. The only disadvantage of this choke is actually resonant. The stray capacitance between the turns determines the resonant frequency of the inductor that's formed by coiling this into 4 turns. And the capacitance of the jacket of coaxial cables is not a tightly controlled parameter among manufacturers or even by the same manufacturer. So it's hard to be sure exactly what frequency this thing's going to be resonant at. You'd like it to be resonant close to 6 meters, doesn't have to be exactly. So that's kind of the thing that's kind of hard to determine for sure as to whether it should be 4 turns or 5 turns for the particular coax you have. So that's a bit of a challenge. You can use a network analyzer to figure out the resonant frequency of a choke that you build in this way. This is a better choke. They're getting to be quite popular. They're made out of ferrite cores that are intended for RFI reduction. And the particular part number that I show here, the DX engineering part number, just below the photograph, these cores fit directly over RG213. And if you slide 20 of these cores over the RG213, it's a very effective choke to keep unwanted signals on the outside shield of the coax cable from getting into the antenna. So this is very effective. It's important for all of these chokes, not only the ferrite choke, let me go back to the previous slide, but also the coiled coax choke. Never, ever fasten these chokes directly to the boom of the antenna because it changes the resonant frequency of the choke and degrades its performance. So you always want to space the choke. I use a couple of inches. You could probably go maybe as little as a ½ inch. You definitely don't need to go 6 inches, but they're always spaced away from the boom. They're never taped directly to the boom. And in the case of the ferrite choke, the same thing. And this is a very high performance choke. K9YC wrote a very well-written paper. The URL to that paper is shown at the bottom of this slide. And this is an especially good choke for very severe RFI environments. If you're in a dense urban area and you've got lots of other 6-meter operators and you really want to get every dB of that possible front to rear ratio off your antenna, this is probably the very best one to use. And this one is also, it's a little bit harder to see in the photograph, but it's also spaced away from the boom, maybe about 1 inch, which I'm sure is fine. Okay, so that covers the antenna part of the presentation. And I'll just spend a few minutes talking about another very important topic, and that is coaxial cable. Good quality coaxial cable really pays off on 6 meters. And the data shown here is feet per dB. It's a little bit different than you usually see. Usually it's dB per 100 feet. but this is feet per dB. It's the same data. So RG8X, and it's probably a good choice for portable operation. Coax cable is probably going to be less than 40 feet, and it's probably fine. For a fixed site where your mast is very close to your home, RG213 is okay. But once you get beyond that, you really should be using a higher performance coax. I prefer to use Andrew LDF4-50. It's readily available at Hamfest, usually for $1 a foot or less. It's getting to be harder to find in the commercial marketplace because the Andrew was purchased by CommScope, and I don't believe they manufacture this particular cable anymore, but there's lots of it out there. And then you might say, well, what about, let's go to 7/8 inch heliax. If 1/2 inch heliax is better, 7/8 must be even more better. Well, look at the bottom of the chart. The length of the coaxial cable feed line has to be 475 feet before your investment in 7/8 heliax buys you 1 dB of improved performance. On EME, yeah, you care about that, but for sporadic E, you probably don't. So LDF4 is really, or any of the other 1/2 inch cables. Cable TV cable is also a very good choice, but that's not readily available anymore. But any of that is a good choice for a home station. RG213, unless you have a mast right next to your house, is probably not a good choice. Coax connectors. I do not recommend on 6 meters that anyone use end connectors. There are too many things that can go wrong. And inevitably, it's going to go wrong right in the middle of one of Lance's EME expeditions, or in the once every 5-year opening we have from the East Coast to New Zealand. End connectors are unreliable. And for 6 meters, there's absolutely no disadvantage to using a high quality UHF connector. Installing both of these connectors requires some skill. So if you don't have that skill, find someone who does. If you can't find anyone, then buy a cable from DX Engineering that has the connectors pre-installed, or from RF Connection. But you definitely want to use high quality connectors. My preference by far is a high quality PL259 UHF connector. Why? It has much more reliable center pin mating force than end connectors. If you have end connectors at home, take a careful look at it. Compare the inside of your end connector, that is the visible part when it's attached to a cable, so the pin, and compare the RF part of that connector to a BNC connector. You might say, well, why do you want to do that? A BNC connector is a low power connector commonly used on the receiving side of things. Well, take a close look. It's exactly the same. There is absolutely no difference between the RF guts of an end connector and a BNC connector. They're exactly the same. And it's, when you take a close look, you can see why there's a problem, because the center pin of an end connector is very small. And if you look at the specifications for the end connector, the specifications specified plus or minus 1/2 millimeter for the depth of that connector when it's mated to the cable. None of us listening to this presentation have the skills to reliably install end connectors and meet those specs, but that's what you really need to achieve. So what I always recommend to those hams who, for whatever reason, still insist that they must use end connectors on 6 meters, use only end connectors that have captive center pins, so that the depth of the pin and its axial alignment is all predetermined by the manufacturer. You really can't mess that up. And any of you who have end connectors in your system that really feel like you really need to leave them there, if you have the old style end connectors where you soldered the center pin onto the coaxial cable center conductor, I will guarantee to you that if you look at those old end connectors, you are going to find that the pin length does not meet the specification. It's either going to be too long, which causes it to damage the mating female connector, or it's going to be too short, which causes extremely low contact pressure, or the pin is not going to be exactly aligned with the body of the connector. If you look at your connectors, you're going to find that problem. And the way to solve it is preferably to get rid of the end connectors altogether, or to use to replace them with captive pin end connectors. And most of the modern end connectors are captive pin. Avoid the use of adapters as much as possible. It's very hard to find the silver-plated adapters now. Actually, much easier to find at Hamfest than currently manufactured. Now, one of the issues with PL259s, and I will guarantee you that almost nobody listening to this presentation does this, especially inside your shack. The performance of the PL259 UHF connector depends on mating force for the shield, so that those little tiny pins along the body of the connector properly engage. And the easiest way to provide reliable mating force for the shield of the coaxial cable, or the outside of the PL259 body, is to simply find a pair of pliers so that you can tighten the shell just enough so that you can't remove the shell by hand. So if you go into your station now, all but one or two of you here are going to discover that you can remove your PL259 connectors by hand. That is not correct. If you can remove your PL259 connectors by hand, you have a potential problem with the reliability of that connector. And this is not fake stuff. I have found it with people who have brought equipment into my station and connected it up and connected the PL259 by hand, and then wonder why the equipment doesn't work right. Well, you didn't tighten the connector enough. And the only reliable way to do that is just to pull out a pair of pliers and tighten the shell just enough so you can't remove the shell by hand. Don't go any more than that, because the shell is somewhat fragile. So if you treat this thing like maybe a plumber would and try to tighten it as much as you can, you may never get that connector off again. But if you tighten it just enough so you can't take it off by hand, you'll be fine, and you'll have a very, very reliable connection. These are the connectors that I recommend, the Amphenol 83-1SP. The name of the manufacturer and the part number is always imprinted on the shell. This is a silver-plated connector, and it's the one I use exclusively everywhere in my station, and it's a very excellent connector for use on 6 meters. Waterproofing. Most of the problems with reliability and maintenance in our station are caused when we build the station, not by the passage of time. And one of the most common problems, and I will guarantee that the vast majority of the people listening to this station have not properly waterproofed the connection of their coaxial cable to the split driven element feed of their antennas. This is what your split feed, what the split end of your coaxial cable should look like. You should see absolutely no trace of the dielectric on the coax cable, no trace whatsoever of the shield. It should all be encased in 4 layers of tape, two wraps of Scotch 33, or if you really want to spend the extra money, Scotch 88. The only difference is the thickness of the tape, with a layer of Scotch 133 of Scotch 130C. I'm sorry, I got that backwards. The Scotch 130C goes at the bottom, and Scotch 33 over the top. The Scotch 130C is not very weather resistant, so the Scotch 33 protects it. So if the connection of your coaxial cable to your antenna does not look like this, you've got a problem, and it's going to develop over time, and it's going to destroy your coaxial cable. And it doesn't take very long on 6 meters for that to be a problem. And how do you know if you've got a problem? If you see any trace of coaxial cable braid or dielectric, and if you don't have 4 layers of tape over the top of it, you have a problem, and it's developing over time. So this is what the center of your antenna should look like. The coax cable should be fastened to the boom, not very far from the antenna, so that it doesn't vibrate excessively in the wind. These solder lugs on the coax cable should not be in direct contact with the aluminum. It will corrode very quickly. So what you see in this photograph is a stainless steel screw through the driven element. the stainless steel screw has a nut that attaches it to the driven element, and then the split feed of the coax cable is attached to the stainless steel screw, but not in direct contact with the aluminum tubing. I like to use nylon insert lock nuts. Nylock is a common trade name. I also use external tooth lock washers, and I've never, ever had one of these connections fail, ever. And when I take them apart, if I take an antenna down, it looks like I just installed it the day before. And I cover the whole thing with liquid electrical tape, so this is what it looks like when it's done. Waterproof and corrosion resistant. And I think this is my last slide. Oops. Yeah, it is my last slide. So this is the tape that I spoke about. Scotch 133 linerless tape. Home Depot carries it. And Scotch Super 33, and everybody carries that. And the way you install this is with, it's amazing when I watch people install electrical tape. You know, you might think that this electrical tape they're installing is made out of gold. And they try to install it with almost no overlap. And electrical tape doesn't work when you install it with almost no overlap. The overlap should be at least 50%. The Scotch 133, you stretch it about 50% of its original width, and the sticky side faces out. Don't believe me? Take a look at the instructions that come with the tape. I prefer Scotch 133 to some of the other rubber tape, and the reason is that it's linerless. Some of the other competing brands have a liner that you must discard, and it's just a pain in the neck up on a tower to be fooling around, not only with the tape, but with this liner that's coming out. So I prefer the linerless tape. It's readily available. It's not terribly expensive. Both the Scotch 133 and the Scotch 33 are overlapped at least 50%. So that's the end of my presentation. I hope everyone has learned at least a little bit. 6 meters is a whole lot of fun year round, but especially in June and July. So back over to net control.
Okay, wow, that's quite the presentation, and I learned a lot today. You know, I thought I knew what was going on, Frank, but you've actually, you know, keep on teaching me new things. And my only this is the Q&A session. I'll start off with the first one. So I've got a pair of those LFAs from Justin. They're the 6-element. They're called the LFA Max. It's not for maximum gain. It's Max, named after a guy called Max, believe it or not. But anyway, that's the one that Justin recommended to me, because in my location, I don't have, I'm in an urban location, so I've got all the worst things. I got mountains to the west of me, and I got valleys to the east of me, and I got buildings all around me. I'm surprised I even get out of the backyard. But anyway, if I stack a pair of antennas, or if I have a 4x4 of 6-element Yagis, how does that affect the that 50-foot Goldilocks height? If you can address that question.
Sure. So I'll just respond to one of your comments. You know, the least effective antenna is one that's not being used. Antennas that are not being used work really badly. But if you're actually on the air using your antenna in an urban environment, it's working a whole lot better than people with ideal locations on the shore of the Chesapeake Bay, or in a flatland rural environment who are not on the air. So enjoy what you've got, and I'm sure you do enjoy it. So to get at your question, when you stack antennas vertically, they have roughly halfway between them what is known as the phase center. It's not exactly halfway. If you want to find out exactly where your phase center is, you can model the antennas in EasyNet, which is now free, and you can find out exactly where the phase center is for your stacked array by matching the elevation pattern for your stacked antennas to the first lobe of a single antenna at roughly the same height as the phase center. But, you know, it really isn't that important to do that. It's fun to do it, but it doesn't really matter. The phase center is very close to halfway between the two stacked antennas. So I would recommend for a too high stack where your main interest is sporadic DXing, I would recommend that you put the phase center of the stacked array at about 50 feet. It's not exactly 50 feet isn't important, but definitely not 70 or 80 feet and definitely not 20 or 30 feet. So think about it that way. I can't imagine why anybody would want to build a 4 Yagi array for use on sporadic E. I think that's more trouble than it's worth. Smaller antennas work very, very well. And I think a better choice if you want to build an antenna for sporadic EDXing is a longer boom Yagi and maybe 2 of those stacked one above the other like JA1BK did in that photograph I showed, rather than going through all of the tremendous amount of effort to build and maintain is a real problem, a 4 Yagi array. Did I answer all your questions?
Yeah, absolutely. That's great. Yeah, the other thing is that my antennas are actually about the bottom one's about 10 feet off the flat roof of my daughter's duplex, and I have a mast that sticks out another 15 feet out of the top of that. And
so how high above the ground is that lower antenna?
Approximately 40 some odd feet. So just under 50 feet, and the top one's probably about 58 feet, something like that.
So I think that's perfect. I wouldn't change a thing. Maybe you could get some heavy equipment and get rid of all those houses around.
Yeah, I was thinking a wrecking ball, you know. Yeah, my neighbors wouldn't like it too much. My daughter would definitely not care. So, anyway.
but you're pretty much above all of those, most of those houses. So, and you know what? Of course, houses have all kinds of nasty stuff in them these days. They have aluminum-backed fiberglass insulation. They have all kinds of plumbing and electrical wiring and internet wiring and on and on and on. So they can be pretty nasty obstacles. But they're not solid metal buildings like they are in an industrial environment. That's really bad. Yeah, if your antenna is tucked down in an industrial environment.
It is what it is, and I got to deal with it.
That's right. It is what it is. Get on the air and enjoy it.
I'm sure there's a lot of
This is Rich K on HTV with another 2 antenna question. I plan to put up a second 7-element Yagi. I've got the first one at 40 feet, and that may not be the final location for it. I do now have a stack match, an OK2 ZAW stack match, which will be installed in the spring. Question is, what would be the heights for the 2 antennas using equal length cables, or I heard that you recommended not putting the stack match box up in at the top of the tower because of not having to climb the tower. So it'll probably go on the bottom with either equal lengths or properly equal phase, you know, so we have that extra half wave. What would be the optimum heights? I was planning on spacing about 19 feet.
Take a look at VE7BQH's charts.
Right.
It will tell you exactly what the optimum spacing is.
Okay. Now, as far as heights now for the 2, with the stack match, which gives me a bip op, either top, bottom, or both in phase, both out of phase. Is there, well, how much I'm trying to figure what's the best spot to put so I have the optimum choice between different angles that might favor me as E-skip incoming angles might change.
Okay, so let me ask you a question. How important is it for you to be able to work E-skip for signals that are only 500 miles away?
Not very. I've got a high LFA at 77 feet for that.
Yeah. Okay. So I would suggest that the antenna you've already installed at 40 feet is pretty good height. I certainly wouldn't recommend that you raise it 2 or 3 more feet. So I would leave the one in place that you've got and take a look at Lionel's chart and mount the other antenna at roughly the spacing that Lionel recommends. You don't have to be exactly that dimension. And he shows 2 figures for spacings. One is the 100% optimum spacing. That gives you the maximum possible gain from the stack. So I would recommend that you use that number rather than the 75% number that he also shows, which gives you a little bit less gain.
Okay, thank you.
Oh, and Rich, I didn't answer another one of your questions. So you implied, maybe you didn't quite ask a direct question, is where should you put the stack match? Well, the absolute ideal place to put it from an electrical point of view is halfway between the two antennas. But I'll guarantee you that when you most want to use that array, somehow you will wind up having hot switched that stack match and it won't be working. And you won't be able to use it. And you'll be forced to climb the tower to either replace the stack match or take it out of the circuit.
It has protection for that purpose, but again, that can always happen, yeah.
Yep, the failures happen. Stuff happens. Yeah, having protection so you can't hot switch it is a really good idea, but relays will fail over time.
Yeah, being almost 80 years old, I don't feel like climbing the tower anymore.
So, and it's going to happen at the time when you're most unhappy, like that once in 5 years ZL opening on 6 meters from the East Coast. So I always place my stack matches on every antenna at eye level on my towers, and then I use exactly the method you described. Either use equal length coax cables from there up to the feed point of each antenna, or you can save a very small amount of performance. And for sporadic DXers, it's a really, really small amount of performance by cutting out a few half wavelengths of coax going to the bottom antenna. But my preference has always been to use exactly identical length cables for non-EME use. That fraction of a dB doesn't matter. For EME use, all of these things kind of go by the wayside where you really care about every fraction of a dB, but for sporadic E, it doesn't matter.
LMR 600 over LMR 400.
Let's go back to this chart. Are my slides still being shown?
Yes.
Yeah.
Okay, so let me go back. So LMR 600 is about the same performance as LDF4. So let's just take a look at that chart. So I think in a future version of this chart, I will include LMR 400 and LMR 600. But the performance of LMR 600 is roughly the same as LDF4. But I'll tell you, I prefer to use hardline cables on my towers. And that is that they're much more resistant to mechanical damage than flexible cables with relatively fragile jackets. Coaxial cable jackets on flexible cable can be damaged mechanically in one of two ways. One is by mishandling at any point from the time the cable was manufactured until it was installed on your tower. And it's very easy for any point in that whole process over a period of many months for a defect to be caused in the jacket of the cable. One very classic one, and I see it all the time with people handling coax cables, if their cable is kind of tangled on the ground and they start just pulling the end of the cable like they're trying to undo a knotted piece of rope. But what always happens there is that this soft jacket of the coax cable is rubbing over the jacket of another turn of that tangled mess, and you wind up creating a divot in the jacket of the cable. You've really got to be careful with these, whether it's LMR 400 or RG213, you're going to be very careful in the handling of that cable. I will guarantee you that if a minor defect has developed in that cable before you install it, water running down that cable is going to find its way into that coax. And on 6 meters, the loss is going to go up rapidly as soon as water gets in. And the other way that flexible jacket coax cables get damaged easily on towers is if they're not taped frequently to the tower face or to the tower leg. At least the cable should be taped to the tower at least every 2 or 3 feet, no more. And why is that? Because it will vibrate in the wind and the jacket will get damaged. And there's a third way that flexible jack cables like RG213 and LMR 400 get damaged, and that is during lightning strikes. If the coax cable is not bonded to the tower at the bottom of the tower and at the top of the tower, a voltage gradient will develop during usually a direct lightning strike. And when the coaxial cable shield arcs to the tower, which it will if there's a voltage difference, it creates pinholes in the coax cable. You probably won't be able to find those pinholes, but I'll guarantee that the water that's going down those coax cables will find the pinholes, and it'll wind up inside the coax and ruin it very quickly. So my preference always on towers is to use a hardline coax, whether it's LDF4 or your other favorite bigger LDF or cable TV cable. And I never use RG213 type cable except at the rotor point. The only advantage I can see to using LMR 600 if you have a rotator involved is you get rid of a few connectors. So you don't have that transition from LDF4 to RG213 around the joint. So there's some trade-offs there, but I really don't like to use flexible cable. My towers get hit by lightning at least once a year, and flexible jacket cables are just not a good idea in that circumstance. Any other questions?
Yeah, Frank, it's K7RJ. I got two questions that are kind of more related to building than anything, you know, on air stuff. You had in fact, while you got the slides up there, you showed about clamping the connectors with some stainless steel bolts and lock washers and so forth. I didn't quite follow that. If you could just, you know.
Was it this slide that you're
No,
about?
it's the one with the nuts and the bolts that were.
Oh, the connection of the coax.
Yeah. There was some sequence you said.
Let me just show a couple of photos.
Yeah.
This is the classic coiled coax connection, and you can see it spaced away from the tower, and you can't really see the details of the connection.
Yeah, that connection we can't quite see.
Yeah. So, but I'll show you one that shows it more clearly. You can kind of see in this one that it's taped up very well, which is a very common problem of people not very carefully taping it up. But this is the image you wanted to see.
Yep, this is the one we're getting close to.
Right.
Yeah,
so this is preparation of the coax before you attach it. Those solder lugs are heavy duty. They're not the kind what you'd use in building a piece of electronic equipment.
Okay.
These are readily available. They're strong.
Yeah.
You had some absolutely no trace of visible braid or coax cable dial.
Yeah, you had the bolt sticking up and lock. That's the one there. Yep. That's the one.
So here's the detail of how that's done. This is a stainless steel screw that passes through the driven element, and after it passes through the driven element, there is a lock washer, and it should be a external tooth lock washer, and then an ordinary stainless nut. So that's snugged up real well.
Got it.
And then the solder lug sits down on the stainless steel nut. So you don't connect it directly to the aluminum.
Yeah, that's the trick there that I wouldn't follow. Okay, that makes sense.
So the lug is not in direct contact to the aluminum. It's in direct contact to the stainless steel screw. And that provides isolation, so you don't have a lot of corrosion buildup at that joint.
That makes sense. I got you.
Okay.
That
would you recommend?
Go ahead.
Would you recommend using Noah locks or any of the other electrical greases on that connection?
I've never found. No, I don't do that. I don't think there would be any problem doing it. It's just not apparent to me that there's any benefit. But you could do that. It's not a problem. And in fact, there is a benefit, and that is stainless steel hardware, and I'm sure many of you have experienced this, has this nasty problem of getting galled.
Yeah.
And you can't take it apart. So with any stainless steel fastener, it's a good idea to put a very light coating of grease, the appropriate grease, so that you don't have this galling issue. And that's especially a problem with U-bolts rather than these small connectors.
Okay, excellent. Thank you, Frank. I have one more, if you don't mind, on the ferrite, the beads.
Oh, but before you get into that question,
yeah.
There's one more step, and that is to cover the whole mess up with liquid electrical tape.
Oh, yeah, you just got some goopy electrical stuff. Yeah.
I didn't want to show only this photo because then you can't see everything else. Okay, so what's your other question?
Okay, the ferrite beads for choke balance. You got 11 or 12 of them or something in there. These guys do the first of all, those are type 31 material? Is that right?
Yeah, type 31. Don't use any other type.
Yeah,
and
okay.
There's the DX engineering part number.
Yeah, I got that. And what about the clamp-on ones? Are those things any good? And they're sure a heck of a lot easier to put on. But because that looks like that's what he's got here.
Yeah, that's what K9YC has done, and this is a very, very high performance choke that he's developed. If you go to his paper, he shows some other alternatives as well.
So the clamp ones work pretty well.
Yeah, and you don't have to use the clamp. You can also use the let's say a round ferrite with maybe a 1-inch diameter opening in the middle, and you can use it the same way. You don't have to use the clamp-on type.
Yeah, the clamp-on's handy because you don't have to. If the connectors won't let you stick through the hole in the bead sometimes.
Yeah, that's right.
The clamp.
And you notice this coax that he used.
Yeah.
Not RG213.
No, that's
smaller coax that's rated for full power. I like to use RG400, which is Teflon.
Yeah, that
coaxial cable.
That's the good stuff. Yeah,
it's rated at 1500 watts, and it's also extremely UV resistant. So that's what I like to use in this kind of a choke. What I use.
Yeah, even though that coax is expensive for a choke, you don't need very much of it.
Yeah, that's right.
Yeah, you're not getting 600 feet of it or something,
Yeah.
Well, I have a question.
Okay,
and I failed to mention when I showed you this chart, it's very easy to make this cable yourself, this choke yourself. Perhaps the most annoying part of it is the shrink tubing that you have to put over the top of it to protect it from moisture. So you can't see the beads in this case because they're encased in that shrink tubing.
How important is that to cover that with the tubing?
I've never done it any other way.
Okay.
So I don't know how. I think the real issue is it possible for ferrite to absorb any moisture at all? And if it does, when it freezes,
it'll rust.
Well, it won't. Rust isn't really the issue.
I understand. I was just joking.
when the temperature goes below freezing, it can crack.
Oh yeah, it could do that.
So this is how I build mine. You can also purchase this choke completely prefabricated from in-off antennas, and the link is shown at the bottom of the page here.
Okay. Hey, thanks, Frank.
Okay.
Frank, what's your favorite way to weatherproof 7/8 Heliax on the outside after putting an Andrew connector on it? Same way, 130C?
Yeah, this way. Yep, this way.
Okay,
yep.
Thank you.
And don't fail to do that, because even though those connectors are supposedly weatherproof, they are not.
Right.
And if you don't do this, you're going to have a problem, and it's a real pain in the butt to repair coax connector that's way up on your tower.
Especially
doesn't cost that much for this tape, and just do it.
What height would I be testing my new antenna? We've tried this is 6-element YU7EF Yagi for 6 meters. We've been trying it various heights. We got it up to 10 feet. We know there's effects around the whole house and everything. But do I have to run it up to the actual tower height of 30 feet to actually get a good knowledge that the antenna is even going to be tuned to the right frequency?
Well, in terms of the tuning of the antenna, as long as it's, let's say, about a half wavelength away from all the metal in your house, it's going to be fine. So in terms of detuning, that's really not an issue if you can get it at least, let's say, 10 feet away from all of the metal in your house. And there's lots of metal in a modern house.
Yeah. Another suggestion is to aim it vertically up, put the reflector on the ground, just aim it up.
Yeah, you could do that to adjust the SWR. But I'll tell you, all these modern antennas, if you all these modern antennas are very, very well designed, and the manuals are very clear. And if you build it exactly the way they tell you to build it, you don't have to adjust it. It's going to be right on the money. As long as you don't have all this metal in your house in very close proximity to the antenna. What's much more important is to try to do this. Get the antenna somewhere in the area of anywhere, ideally 50 feet high. If you can't do that, 25 feet high. You only give up 3 dB if you're at 25 feet high. That's, you know, like I said, it's a whole lot more important to be on the air than to squeak out those last couple of dB but not be on the air. Any other questions?
Yeah, I left some comments, but they're not answered, so I'll pester people. I learned today that there is a separate program to go with EasyNet. It's called Auto EZ. It makes it user-friendly and easy to go through all the features. It's by Dan AC6LA. Is anybody using that?
Yeah, Steve, my friend Mike up in Prescott uses that. He's become kind of an expert on it. In fact, he's one of the guys that he consulted with, and he loves it. It's amazing. It is way, way worthwhile if you want to get a little more serious about designing. But yeah.
But I'll tell you, it's YU7EF's designs are very easy to duplicate, and I've never found it necessary to fool around with EasyNet to try to do better than the YU7EF designs. They are just incredible, right out of the description.
Frank, I've got 2 questions for you about building.
Yeah, go ahead. This is Lance.
Yeah, this is W7GJ, Lance. When you build a YU7EF Yagi mounting on those high density polyethylene plates or something like that, you referenced that you use stainless steel U-bolts to hold the elements onto the plastic plate. Where do you get those?
Okay, so let me repeat again what I do. So these are the Stauf clamps readily available from many sources, and I use stainless steel screws to connect these 2 halves of the Stauf clamp together, and they are fastened to a plate. Now, most hams use an aluminum plate. I do not use an aluminum plate. I use a phenolic plate. It's a 100-year-old type of plastic, readily available from many industrial sources. So, and then that phenolic plate, in the case of my antennas, is connected to the boom using a pair of, and I use galvanized steel U-bolts.
I see. So this, the way this clamps down it on the element itself, and the 2 screws that hold that together don't touch, they don't need to go through the plate at all. The mounts it to the boom, right?
Yeah, so the 2 screws that, in the next version of this presentation, I'll show the whole assembly rather than just this part. But it's very simple. So if you can just imagine at the bottom of this pair of halves of the clamp, there is a flat plate. And in most ham antennas, that flat plate would be made out of aluminum. And these clamps are attached to that flat plate using screws that are long enough to go through the clamps and through the plate. So these are attached to the plate with those 2 screws. And then the plate, as has been done by hams for decades, is attached to the boom using a pair of U-bolts.
Hey, can I add something to this? Or you go ahead. I'm sorry.
No, go ahead, Ron.
So Lance, let me just make one more comment.
Yeah.
I'm sure the way hams have built, the way hams have connected Yagi elements to booms for time immemorial is to use 2 U-bolts around the element, and then a flat plate, and then 2 U-bolts around the boom, right? So this is exactly the same thing. except instead of using U-bolts around the element, it uses these stout plastic clamps. Other than it's the same idea. And of course, the other thing that is getting to be very popular for 6-meter antennas especially is to use this square aluminum tubing. So in that case, you don't need U-bolts at all. You can just bolt that plate directly to the square aluminum tubing. And that square aluminum tubing is readily available now.
Yeah, Lance, on my YU7EF, I'm using some stainless steel U-bolts to go up through my plastic insulator base. And they have a metal saddle block built in, patented, I guess, by DX Engineering. And they work great. Of course, it's for a round boom, so you have to make sure it doesn't get too loosened up. You want it clamped tightly. But those work great, and they're not super expensive.
Unrelated, this is not for holding the boom, the elements on, but for spacing the coax away, the feed line away from the boom. Yeah, that distance that you're called space the choke. I 3D printed this kind of a deal. This goes around the boom, and this goes around the coax. And
very nice. Very nice. Yep. As long as it's, I hope it's very UV resistant.
Yeah, it's PETG. It's supposedly, supposedly UV resistant. Yeah. So we'll see.
there's a lot of ways to do this.
Yeah. Oh, yeah. I just did this. Yeah. I just did this the other day, so I happen to have it here, so to show it off.
There's a lot of ways to do it. There's nothing electrically significant in terms of the way you do it. It just
there's just a piece of plastic cable. And the bolts go in here. There's no, Anyway,
if you notice in this photograph, this particular choke is fastened to the boom using tie wraps.
Yep. My thing is
I've never seen a tie wrap that lasts more than a few years.
Yeah, I expect these will last. I hope. Yeah, presumably the write-up on this kind of material is very good. It's almost specifically for UV and bad weather.
I like to build my antennas so I don't ever have to touch them.
I like to build them once. I don't want to move on and build another antenna. I don't want to rebuild the same one.
As I mentioned with maintenance, almost all of the maintenance problems with any antenna were created during the time the antenna was built and installed.
I'll tell you, people up north that worry about the snow and wind, those are wimps. This dang UV from the Arizona sun will kill anything.
Anything except stainless or aluminum.
Oh, I'll tell you.
Yeah, and I suspect these stuff clamps, the ones I've shown here, these green ones, those in a really bad UV environment, like in Arizona or Texas or Florida, they might have some survival issues. I've never had a problem in Maryland.
Yeah, try it.
Frank, I have one other question for you, and that's on your 11 element Yagi. Yeah. How did you build the boom?
It's 3-inch diameter, 1/8-inch wall, 60 feet long. Two 24-foot pieces and a 12-foot piece.
Okay, so it's not tapered.
No. But this is a big beefy tower, so it doesn't matter.
Okay, thanks.
This tower is a 150-foot rotating tower. And there was a blank spot at 50 feet, perfect place for this antenna. Put it there and it is great. And let me mention one other thing. I need to put this in a future presentation as well. You will occasionally see this when people have side-mounted Yagi antennas on a tower. You never want to place the parasitic elements very close to the tower face, because the tower face will detune the elements in exactly the same way that placing a parasitic element very close to the boom of a Yagi will detune it as well. The exact same thing happens when a parasitic element is very close to the tower face. This 11 element Yagi, that space between those two parasitic elements is probably roughly about 6 feet, and the tower is centered in that space. It might even be more like 8 feet. But you definitely never, never, ever want to put a parasitic element for any Yagi on any band within less than a foot of a tower face. You might get away with it with Rome 25, which is small tower, but you put a parasitic element like that close to the tower face and it gets detuned. And it's not detuned by something called by parasitic effects that we're familiar with modeling. It's actually eddy currents. It's eddy currents that cause problems with parasitic elements very close to booms, and it's also eddy currents that detune parasitic elements that are very close to a tower face.
That's great, Frank, and thank you very much for all your help here tonight. We've kept you way beyond what I expected you to be on here. It's probably getting close to 11 o'clock your time.
I'm not worried. If anyone has a pressing question, I'll be happy to address it. Otherwise, I'll probably watch TV for an hour.
Oh my gosh, catch the news. All right, guys, thank you very much. And I'm going to post this whole presentation video to YouTube probably next day or so. And you can get access to it through the Front Range 6 Meter Group YouTube page.
I'm always happy to accept and respond to questions at my email address, which is shown here.
Awesome. Thank you. Thanks, guys.
Thanks, Frank.
Okay, good night,
Thanks,
everybody.
Frank.
73.
Bye-bye.